Um, I'll be trying to do a little bit of coding with you today. Hopefully this all works out. Usually live demos are already hard enough. Trying to code something with an audience is even harder, but we'll see how far we get. But just so I have a little bit of an idea, in this room, who's familiar with Solidity? Okay. Who would say they're comfortable writing an implementation of a payment channel? Okay, good. Who's heard of Libp2p? Good. All right. So I'll dive right into it. Maybe if you want to play around with the code, let me actually switch to this slide first. I don't know how well Wi-Fi's been working, but try to go here first. Check it out.
GitHub has been having
yeah, GitHub has. Yeah, actually, I hope my code changes were pushed. Yeah, I know. The whole tech world stands still. At least Git is decentralized, right? But GitHub isn't. Yeah, so you can do this, and then actually. Maybe I'll just write down the URL, please. Okay, and the second thing is because this is, I made everything with JavaScript. I usually work with Go, so a lot of this stuff is new for me as well. Like the JavaScript side is new for me as well. But one thing with JavaScript is always you have 1,000 dependencies, and downloading them takes a while. So if you want to prepare, this will probably make it easier. The repository that you'll check out will have two folders: contracts and node. Contracts is Solidity stuff. The node is a little REST Express.js REST app. So just go into these two folders and check out the code. Install the dependencies so that you don't have to wait however long it takes depending on Wi-Fi. And then I'll start with a quick introduction. My name's Lucas. I'm one of the co-founders of Centrifuge. I'll give you a little bit of detail about what we do, so you have a bit of a background. Centrifuge is a decentralized protocol to allow to enable like the financial supply chain. So what does this mean? Companies today work with send invoices, receive purchase orders, send shipping notifications, all these things. There's really there's no standard for this. Like it's worst case a fax or a letter. Best case, like some companies use some sort of XML interface to like send data back and forth, but none of these are like actually cryptographically verifiable messages. But of course, these essentially represent contracts, business transactions. So what we're working on is we're working on a way for two companies to exchange these documents in a secure and private way, giving both sides of the transaction a way to further down make claims about these documents, like have signatures that you can verify. So we use the two core protocols we're based on is Ethereum and Libp2p. We have a privacy layer, so to speak, or essentially this is like our layer 2, where we do most of the heavy lifting. So in the on-chain world, we have identities. So basically, I am Lucas, and this is my public key. Anything anything I sign with the private key to this public key is mine. And then we also use a blockchain for basically committing to what the state is, so that you have a timestamp. Of when this transaction was signed, when it was agreed upon, which is somewhat important in like many business documents, right? Like if you create an invoice, you want to make sure that 30 days later you can remind the customer and charge them a fee if they're paying late or things like that. What we do off-chain is all of the heavy lifting for two big reasons. Something like an invoice is a fairly complex document that can be easily kilobytes in size. Like if I place an order for 1,000 items and I want you to deliver these 1,000 items to 50 different addresses, and like imagine the size of whatever would be that blob that you would put on chain. Probably not feasible for much more than a few transactions a minute on Ethereum. And the other reason is, well, these like businesses in essence, they treat all of the financial information as a relatively private thing. I would say in general in the Ethereum in the blockchain world, like we haven't really faced this challenge yet, maybe because we haven't reached the usability or the popularity that we want, but like privacy is going to become overall a really important thing, right? Like right now I don't care about who knows what kind of kitties I own, but as soon as there's something like anything that touches my health records, my salary, how much I spend, things like my pattern, like if I go to a coffee shop every other day and I make a payment there, well, that gives an advertiser or like a credit rating agency, or even worse if it's a bar or a club where I go every weekend, like will give like the health insurance company like an advantage to like say, oh, this guy's probably like not as healthy as he should be, maybe we're going to charge him more, or like all sorts of different negative things, right? And so with going off chain, we solve this privacy problem. Essentially, this is what it looks like, right? There's a peer-to-peer protocol with Libp2p based on Libp2p, and then the public keys are committed on chain. Libp2p, and so this is where it becomes really nice, is it has a, so this is called the SecIO module, which is essentially comparable to SSL. So if you think of like going to an SSL encrypted website, there's a key exchange to agree on a encryption key for the session. You do that by signing with a Diffie-Hellman key exchange. And so Libp2p SecIO basically does this, so that when you're saying I want to connect node to node with public key X, this key exchange will ensure that the only person you're ever going to talk to is whoever has the private key to that public key. So you get the same kind of safety that you would with an SSL with like an SSL connection. Then what we do is, and this is something that is not really relevant to payment channels anymore, but important in our business case, because we don't really have simple payment channels, but we have like complex documents, and the order. So for us, like order and timing matters. So every time the state gets updated, we don't commit the entire amount of data, but we commit to a hash on chain, so that you get a proof that this is the state at point X. A little bit about this Merkle root. Sorry, a little bit about this state commitment is the Merkle tree, of course. So instead of just taking our documents, like say an invoice, hashing it, we essentially have a state tree per transaction or per document, sort of per channel, where like each individual field is a leaf in the tree, which gives us this really cool property where which is what we call precise proofs. there's a, on Centrifuge, on GitHub/Centrifuge/precise proofs, there's a Go implementation of this, where like you can take an arbitrarily structured document, you generated a Merkle tree out of it in a predefined way, and then you can do things such as, with this Merkle root of X, I can prove to you that this is an invoice of amount $1,500, but I'm not going to disclose to you who the buyer is, who the supplier is, and what the due date is. So, so with these proofs, like Merkle trees are usually used just to prove membership in sets. We encode our documents in a Merkle tree, so we can selectively share certain properties with a third party that was not initially a member of a channel or was not part of that transaction. So I can go to for example, I could go to a decentralized bank that would want to verify that I have approved invoices that they can finance, and I can show them what my revenue is without having to tell them what exactly the secret ingredients are I'm selling to Coca-Cola to make their beverages or these kind of things. Yeah, so that's yeah. So this is the GitHub link, just in case you're interested. Though we won't talk about this much more than that. But so let's get into the content of the actual workshop. So state channels. I asked the question before. What are they? Quick introduction to Libp2p, and then we'll do some like Solidity smart contract development, and then we'll look at channel settlement. So a state channel, of course, it begins with Alice and Bob. So I'm talking about this particular subgroup of state channels. You can essentially turn anything into a state channel. I'll talk specifically about a payment channel where the main objective is to move money, tokens, anything between two different parties. So the way this works is you have an escrow contract or a channel manager where both Alice and Bob deposit an amount of money that they can then transfer between. And so every time you update the state, basically you don't actually commit the fact that this transaction happened to the channel contract. What you do instead is you just give this message off protocol or off chain to Alice saying, Bob says here, one of my money bags is now yours. The way you do this is, well, so going back to this channel concept, right? Both Alice and Bob can update the channel at any point in time, but the only valid updates are obviously the ones where I make an update that economically is worse for me. I can't make an update to this channel where I say my counterparty, I'm taking one token from my counterparty. I can only say I'm giving my counterparty one token. So what you usually do is you usually just fund them with an equal amount, and then if I want to send my counterparty tokens, then I would basically reduce my part of the total amount held in this contract and assign more to my counterparty and vice versa. Yeah, so Alice can only reduce her balance, Bob can only reduce his balance. So cryptographic signatures, I think I don't need to go into this really. Okay. So what we do is whenever you make an update, you sign a statement with your private key. I say, okay, the balance is now 4 instead of 3 for Alice. So Bob essentially moves one token over. So now this goes back and forth. Bob makes another payment to Alice. He signs a new statement that says, my balance is sorry, your balance, Alice, is 5. Now Alice needs to make a payment to Bob. she needs to pay actually 3. So Alice signs a statement that's saying, well, now my balance is 2. Sorry. So when you're done with moving money back and forth, you're basically settling. So the channel contract has a way to accept the settlement, which is basically it verifies that there's a statement, a state update that says how much should be paid to Alice, how much should be paid to Bob. So now this in theory works great. If everyone plays along, you just take the latest update, the latest state update, and you commit it, or you submit it to the contract. But of course, like now, if Alice is not as nice as she's supposed to be, she could take, instead of trying to settle the contract with the latest update, which is this one, she could try to sign with something that's a previous update, right? So here her balance was 4, or even better, she could try to settle with this statement. So what she can do is she could try to submit this, and then like obviously the contract needs a way to make sure that only the latest state update is accepted. And so what you do is you use a nonce, right? So you have a counter that just increments every time. So whenever I update the state, I just increment, and basically by incrementing the counter by 1, I'm saying any previous signed statement I've made with a lower nonce is invalid. Now this is the new statement. So you do this. You just add this nonce. It's included as part of the cryptographic signature. That's basically that this message has. And now the contract gets a little bit more complex. Instead of just settling immediately when you submit a transaction, or when you submit a state update, you have a delay. You say, okay, Alice submits the balance of 2 with nonce 3. It says 2 is for Alice, 4 is for Bob, which is fine. If Alice would have, however, would try to settle with the previous update, the contract would announce the settlement, would have the state of, like, I call this a pending settlement. It says the current nonce is 2. The split is 5-1. Now, when Alice does that, Bob basically has to monitor the channel contract, and when he sees that Alice is trying to exit with an invalid state, he can submit a nonce, an updated message that has the more recent balance, and because this so nonce 3 is higher than 2, so simple, the contract discards the previous settlement, now starts a delay, or basically every time you submit a settlement, you start a timer, so that your counterparty has time to react. Once that time is up, it'll accept the last settlement sort of instruction it got, and then you can request to withdraw your funds. So once this timer has elapsed, there's just a simple finalizing the transaction. You just then the funds get dispersed to the members. However, it was what the final balance was. So what does that mean? A message that I send for a state update, it needs to make sure that you reduce your own balance, right? So I can't. A valid state update is not if I'm taking from my counterparty. It must include an increased nonce, and you must sign it with your key, so that later on you can verify. That you actually made this update, of course. when settling a channel, so this is what the contract does. So you need to prove that your state update is based. So okay, I need to go back a little bit. So basically, what you need to do is you need to prove that your state update that you're pushing is either a state update that your counterparty has made, because that basically means that Alice and Bob. Alice sends an update to Bob. If Bob submits that update or makes an update that came after that update, then he can settle with that update, because coming from Alice, it's obvious both parties have agreed to the state. Alice initially signed it. Bob accepted to submit it. The contract needs to make sure that you submit the most recent known state. So that's why we have the delay, in case you don't submit either you didn't get the most recent state update, or you maliciously tried to submit a previous state update. There's this time delay so that your counterparty can submit its own claim with a more recent state. And then you request the final settlement. So this is what happens in a very simplified way on Ethereum in like the MVP payment channel. So going into Libp2p, Libp2p is a technology or a stack, a tool of standards and implementations. It was initially started by the guys at Protocol Labs. I don't know if there's anyone here from Protocol Labs. No. Okay. So Filecoin, Filecoin IPFS is based on that. It was so when you access a file with IPFS, you're using Libp2p under the hood. It has fairly stable implementations in Go, Rust, and JavaScript. They're not perfect. There's definitely some areas that are still very much still very dynamic, and so definitely spend some time like reading up on like what versions play well together, what is tested, what features you really want to use are actually available. So as I said, most of our experiences with Go, so to go back to like what we do with Centrifuge, our documents are, we actually use protobuf, which is a binary format to define the schema of our documents. And so with Libp2p we send gRPC, which are the RPC calls that protobuf has across a Libp2p channel. So this is what I'm most familiar with. Parity and Polkadot, or Parity Substrate, is based on Rust. So they've been pushing the Rust development, the Rust roadmap of Libp2p quite a bit. I think Parity Substrate uses Libp2p. I think there's even a prototype of Ethereum with Libp2p. I think written by Rust, or I'm not sure. So a few interesting projects. The cool thing is some of the JavaScript stuff actually works in browser. So obviously you can't open arbitrary like ports on your firewall and can communicate over UDP with a remote host or a remote node, but you can use WebRTC, for example, to have peer-to-peer connection from the browser to any other node that supports WebRTC. I've mentioned SecIO, which is really handy, so you don't need to worry about authenticating your counterparty. And then, like one of the things I sadly won't have time to get into in the workshop is the distributed hash table. So essentially, when you're building your peer-to-peer network, there needs to be a way to discover other nodes. So all of Libp2p is it's a bit of an advantage and a disadvantage, but there's probably like 150 GitHub repositories for Libp2p, probably 50 in each programming language. It's very pluggable, many different modules. It takes some time to wrap your head around it, but the way that you can discover different peers is you can either do it completely manually, like you just hardcode the URL, so it uses its own URL format under the hood, or you can have a setup with a distributed hash table with some sort of boot nodes where you just flood all of the discovery messages to the entire network, and every node maintains its own map of the network. You can also have anything that you fancy. For WebRTC, for example, you still need to use some sort of rendezvous server, so you have to think of a way you do that. But the distributed hash table is quite handy. My colleague Miguel, and I have a link later, he did a rock paper scissors implementation in Go with Libp2p. So if you're interested in like seeing just what the minimum implementation of a DHT with like simple communication back and forth is without all the fancy payment channel stuff, I'll share the link with you later. I encourage you to check it out. It does like NAT hole punching. I actually luckily haven't had to deal with that yet, so don't ask me any questions, but I know it somewhat works. Sometimes it doesn't. I mean, but so you can install those modules, and then it has some features for like routing and protocol translation. So you can have one. I think there's a Tor module where you can have a hidden service that basically just acts as like one peer-to-peer, like P2P node on the other end that does like translation into, for example, WebRTC or like UDP, TCP, whatever you fancy. You could probably implement your own network transfer protocol on SMS or who knows what. So you can, and it has this built-in way that of like using intermediate nodes to go to jump from one protocol, like one network protocol to the other, and the entire and it on the application layer where you're, so by application layer I mean like when I'm interacting with the channel, when I'm using it to transmit information, then I don't need to worry about all these transitions. So Libp2p, that's mostly it. I think I'm getting ready to start looking at the code. So before that, there was a lot of information. Are there any questions so far? Yeah.
So when Alice and Bob made statements and sent tokens to each other, were these exchanges monitored or seen by the channel? Because if they want to settle later and the channel has seen all the transactions, why does Alice or Bob need to include the current balance?
No, so the, let me go back to this. So this contract, it was maybe the graphic was a bit too abstract. This is the Ethereum contract that just worries about initial deposit, and then you submit a update for settlement. So you can take any message that was exchanged off chain and submit that to settle the channel. Okay. So anything that happens off chain doesn't touch this contract. In fact, it shouldn't, right? So you get this whole scalability benefit, and in some ways also privacy benefit, that whatever you send back and forth, you can do 10,000 updates here. Like the only thing that costs you something on chain is opening the channel and settling the channel.
Okay, good. Thank you.
So I'll start. So let's get back to the code. You will need Node.js, npm, and curl. Hope that's okay. The way I've set it up is there's a config.js file in Node that has all of the wallets and stuff configured. In contracts, you can run you can run npm run Ganache, which starts a Ganache, which is Ethereum, like one of the Ethereum like developments, like local. It used to be called test RPC, so just a local blockchain to test to basically not deal with any real live chain. So it starts Ganache with a predefined mnemonic, which is configured in the config. So if you run it this way, you can also deploy this code on your own contract, but then you need to set up all of the wallets and private keys and stuff. If you do that, basically your node will be able to work with the contracts and Ganache that's running. I also made the code, so I built a bit of a skeleton, and I just configured it so that if you have an environment variable where you define Alice or Bob, it'll start out with one configuration or the other, and so to talk to each other, it'll be a little bit simpler. Calls.sh has all of the curl commands to interact with the node. Ports you need locally. I think Alice is 3000 and Bob is 3001 for the REST API. 10333 is the default Libp2p port for TCP connections, which is Alice and Bob is on 54, and Ganache runs on 85 and 8545. I've shown you this before, so if you install the dependencies both in contracts and in code, you can start working on. You can start actually running the code and the contracts. Were there any problems so far with the code? Okay. So let's look at what we have. Oh yeah, so this is so you can start Ganache. You can already do that now. Just open a separate terminal, screen, tab, whatever, and start Ganache. It will run with the network ID and the ports and the so if you have any questions, just interrupt me at any time. I mentioned so what we're going to do is we're going to work on the channel manager contract. Time-wise, I've had to shorten this to 1 hour instead of 2 hours, so I'll have to see how much we get to actually looking at the Libp2p network transfer. But we'll start with the actual settlement, which I think is on-chain the most interesting component. The channel manager contract has four main methods. First of all, you create the channel, so you define the balance and who A and B is. So basically, just two wallets, an amount, and the kind of ERC20 token you're using. Then both parties have to fund the channel, and then basically the channel becomes active. So in this implementation, like it never expires. Don't ever try to use this code in anything for production. Of course, I shouldn't have to say that, but this is just a simple proof of concept. So obviously, this is not secure. And doesn't handle a lot of the edge cases, so basically you fund, then you settle. So this is what we'll go through, and then once the settlement period has elapsed, no claims have been made about like newer state updates, then you can release the funds, which will return the funds back to the users. This is so contract/channel manager dot solidity. I've set up the scaffolding. Coming back to this, so I've set up the scaffolding to mostly implement this, mostly implement these two. So we're going to look at the settle method. I'll walk you through the methods that exist on the channel, just so you have a bit of an idea what happens. basically in the create channel, as I said, you assign it an ID. You say 2 addresses, which are the 2 parties, the ERC20 token you're using, and the balance. Like, of course, you check if the channel is taken. You need to make sure that you have decent proper addresses. It's about all the validation I do for now. Of course, you could do more, and we probably should do more. But then we just use this storage struct to store this information in this channel manager contract. So you have this is where the channel information gets stored. So that's creating a channel. Funding a channel is relatively simple as well. We have some sanity checks, so we only allow to go back to this. You have like a channel status. Basically, it starts with initialized. If party A or party B fund, it just says that it has been partially funded. Once both parties have funded it, it gets to active. If someone requests to settle the transaction, this is basically when the counter starts ticking. It goes to pending settlement, and then once it's closed, it's settled. So funding, of course, we only allow an initialized channel or a partially funded channel, and we make sure that only the we just always require the sender to be either party A or party B. And then what we do is we request, so this is the currency is the ERC20 token that we're going to use, and in this example, I just took the OpenZeppelin ERC20 token, and it's getting deployed automatically if you run truffle migrate I think it's called test token. So you'll have like a test token contract that's just an ERC20 token where actually the deployer can mint tokens. So you just mint tokens for you, and then we can play around with them. So it tries to transfer from the currency to the channel the balance, and then it updates the state accordingly. Then the withdraw, also relatively simple. You check that either the sender is either authorized party on the channel. You make sure that it's been in pending settlement, and so actually this wasn't shown on the previous slide, but the channel has a settlement block, plus this is a static variable, block timeout, where we just say the channel is in pending settlement for X number of blocks. Once no update has been made to the settlement request for X blocks, we allow you to withdraw. So basically, once the settlement block plus block timeout is less than the current block, we allow the contract to proceed, and then we transfer the. And so I just store one balance. So basically, on the contract we store channel A, balance A. We transfer the balance A to party A, and we transfer the balance B, which is twice the channel balance minus balance A, to party B. We set it to withdrawn, and then that's it. So questions up until now. So we're going to look at the settle channel, right? I've mentioned this before, and so maybe we can start building this step by step. The settlement conditions are as following. But you only allow settlement of non-settled channels. The nonce must be increased. The balance obviously can't be more than the total channel amount, because otherwise you could withdraw more money from the contract than what you initially put in, and you verify the signature. For simplicity, I made this easier to, I made it slightly simpler. So instead of saying that Alice and Bob make updates, let's assume Bob made the last update. It means that if Bob wants to settle this channel, Bob would have to couldn't submit his own update without proving that his own update was made based on a previous update that was made by Alice. Because if not, you have the problem that basically Bob can just claim nonce 1 million is my balance, and Alice would then be unable to say, yeah, but actually this is completely false. I never actually gave you that much, and she would have no way of just saying, yeah, like there was at no point in time was Bob actually moving money or had this money, right? So if you go back to, let's go to this. So if you run into this problem where if I can just make an update, if I can submit an update that I've made myself, then I need to prove that in this update I've only reduced my balance. And the way I would prove this is by showing the previous update where it says that Alice gave Bob the funds, right? So fictional scenario, 10 tokens on each side. Now I want to submit an update that says I now have 15 tokens. This is the current state. My counterparty, I would need to prove that first, because I now have 15. I need to prove, of course, that Alice, or that my counterparty gave me 5 tokens first. So I would need to prove that Alice at some point said, your balance goes from 10 to 15, and then I can say, or from 10 to 18, and then I can say, okay, and now my update is I'm reducing my balance from 18 to 15, and now I can settle this transaction where I say I'm reducing my balance from 18 to 15 only if I can prove that Alice at some point agreed to my balance being 15, because otherwise how would you know whether at some point in time my balance actually was 15? So we skip all that in this implementation by saying Bob can only settle with an update by Alice, and Alice can only settle with an update by Bob. So basically it means that whatever I'm settling with is guaranteed to be true by the is guaranteed to be correct by the counterparty. So Alice would so I can only settle with a valid update by my counterparty. So there would never be this problem that I could fake some sort of update. And then if I made other updates, then my counterpart my counterparty makes an update, and then I reduce my balance after that and give my counterparty more. The counterparty could take this update and settle, because again, this then would be my counterparty settling with an update that I've made where I agree to the current balance, which is worse than the previous balance.
If they have to update twice in a row?
So what you do is, simplest case is you only increase the nonce every time it switches from A to B, right? So if I make 5 updates, if I make an update first that says your balance is 10, and then I make another update that says your balance is 11, and then I make an update that says your balance is 12, right? Those can have all the same nonsense, because it's in the best interest of your counterparty to then take the one that says your balance is 12. And if there's a one with the same nonce where it's like your balance is 11, then that doesn't matter. Although there's also like some things you need to watch out there, but essentially that's what you can do. So yes. So let's look at the code. Okay, it's actually big enough. Let's see. Right, very nice. so this is you're in master. So let's look at the contract. Great. Right. So this is the method we want to update. This is the method we essentially want to write. So I'll switch back and forth between the presentation now. But so what we need to do in this method is we need to verify that these conditions are met. So let's start with the simple one. Well, I have the first check I have in here. Alice or Bob needs, or party A and party B need, either one of them should be the sender. Then we have to make sure that that channels are not settled yet. So basically what we require a state where it's either active right now or there's a pending settlement. Then the next step is we want to make sure that the nonce is increased, right? So actually, okay, sorry, I saw that bad work on the slides. So what we make sure is we validate that the total balance of A. So I have 15 minutes more. Okay, so how would you guys like to do it? I have 15 minutes, so I think we can get through the settlement transaction and then look at some other stuff. If you want to try to code this or play around with it, you can. I think I'll just sort of walk through this code, and then if you have any questions about it, let me know. And then there's actually a secret second branch that's called settlement. No, sorry, it's actually I renamed it on GitHub to something else. Finish settled transaction. So if you want to at any point in time look at the code that actually implements it, just check out this branch and you'll see it.
That's actually
It's the same as master.
Yeah.
Really?
We did
Yeah,
not
master
take
has the
Shit.
code already.
Master? I didn't push. Oh no.
What's the commit message? Is the one we should be looking at?
Good, I push it. This is not. Alright. Well, forget what you saw and pull again. Of course, I built it first and then didn't push the deletion. Yeah, so so we check that the balance is a sane amount, and then here we make sure that the nonce is increased. So so every time we receive an update, we store in the contract that the nonce is now X, and any future update has to increase the nonce. Then we check that we basically define the counterparty. Say like if you're party A, your counterparty is party B. If you are party B, then your counterparty is party A. And then we use this variable later. Now we get to the interesting part. Who has signed stuff on Ethereum before? Like transactions instead of, okay. So basically every transaction on Ethereum you sign, but usually like Web3 JS or whatever you're using, it does all that, right? But the same, but you can actually access the lower level functions to create those signatures for anything that you want, really. Kekok is the, I don't know how you pronounce that, but is the hash function that is used in Ethereum. There's some particular things about how Ethereum signatures work. So for the way this, let's see. So what I'm using here is the OpenZeppelin ECDSA module. As it has two very simple methods. First thing it does is it has this 2 ETH signed message hash. The way standard Ethereum signatures are made, so the reason we do this is to be compatible with when you use MetaMask.sign or Web3.sign, which basically what you do is you hash the payload, then you prefix it with a certain string, the length of the hash, and then you sign that. So what we sign is ABI encode pack basically just puts all of these variables and puts them in one byte array. And so what you do is you sign the channel ID, the nonce of the state update and what the balance was, along with and so this is maybe a bit confusing, but along with the counterparty, because basically the signature we're trying to verify is that let's assume I'm Bob. Alice has sent me an update for channel X with nonce Y and balance Z, and it was made by Alice. And so then we pack all of this together. We create the signed message, and then this dot recover, it calls like some eternal solidity functions. Let me this one. So what it does is it implements the elliptic curve like signature verification that is used for Ethereum transactions, and it works with your address, with your private keys that you use in Ethereum. So what it does is, I won't go into the details of this, but what you do is you call .recover and you pass in the signature, and it'll take the message and the signature and deduce the public key that was used, or the public key that belongs to the public private key pair that was used to generate the signature. So in the end, what you get back is you get the signer, and so what you need to make sure is that if the signature is valid, the signer address should match the counterparty. So Alice in my example. So once you've done that, you've basically verified. So this is our state update. Anything that I would transmit to my counterparty are like these 4 variables. Well, I mean, essentially, you transmit. This is a kind of obvious, of course, but you transmit the channel ID, the nonce, and the balance. You attach the counterparty just to make sure that you can't reuse updates. I mean, you can't reuse updates across different channels or who knows what. And then you recover the signature, and so if that message that you calculate here matches what was signed with the correct private key, then in the end you get the signer, which should match the counterparty. So by then you know that this was a valid update. So we know it's a valid update. So we increase the nonce to the current nonce. We set the balance. We set the block number to the current block, so the clock basically gets reset, and now you have more. Now the counter starts again, and we set the channel to pending settlement, so that you can require a withdrawal.
So the message at the top needs to be exactly the same format as the messages exchanged between Alice and Bob. Yeah.
Mm-hmm.
Right.
Yeah. So essentially, this is a bytes 32. So 256 bits. This is a uint32, and this is a uint 32 as well. Those are 0 prefixed. So they're it's a fixed length binary blob. This message. And so when you're passing the message, you don't necessarily need to pass this message along, but when you sign, you need to sign this, right? So I can give you a JSON with the different attributes, but the signature must be of precisely this. Otherwise, it won't work. Yeah. So yeah, this is basically what happens on chain. Now, let's see. So the I have two nodes running. This is Bob. Blue is Bob. Yellow is Alice. So this and I have like 5 more minutes, so I won't have too much to show. But basically, if you want to play around with it, I have this cat calls. I have this calls.sh script with just some interactions on the Node.js application, which I haven't had time to show you at all. But basically, it interacts with the smart contracts. So what we can do is we can create the channel. You fund it, and then the counterparty needs to join. And then this is where we would start coding the actual creating the message. So I'll just I guess because I really want to show you what happens on the peer-to-peer side. I'll show you some code and we'll do like some improvised demoing, but so so I have this is basically what you call mostly relatively boring JavaScript REST API stuff. So this is the update for a channel. So we basically have the amount. We get the channel state from Ethereum. We make sure that you can't update anything with stupid data. We make sure the channel is active. We increase the nonce on our end. We set the balance to the amount. And then we and so this is so I was so I would have liked to actually code this with you, but time-wise it doesn't work. I can already spot the bug in this implementation, but anyway. So here's what we do. We have this message string function, which is an implementation of the same thing that we do on the Solidity side. So we do hex to bytes. We make sure that this stuff is padded. We just append first the channel, the nonce, balance, and then the sender. Actually, this should probably be also hex to bytes anyway. And then what we do is we sign this message. So web3.eth.sign, as I mentioned before, the signature that you create with Web3.js. That's that method. So it takes your private key, signs whatever you pass it, and returns the signature, which is a 64-byte signature. And then what you do is we do that in a message. We put that into a JSON blob, and we call out to my little peer-to-peer module, which I will show you right now. So for the JavaScript version, I mostly relied on actually the where is it? Mostly relied on the JavaScript Libp2p, not the crypto module, but on these examples, which actually are quite helpful in just figuring out how it works. So like you have just very simple example showing a set of different features. I killed my terminal earlier. So you start a listener. You get your peer ID, which so I have this configuration which just includes a public-private key pair. I tell it which TCP port I want it to listen on, and then it starts listening to anything on message. And so on this end we would need to so this end actually the next step would be to implement storing the message on the counterparty. So if Alice sends an update to Bob, Bob needs to store it. So this is what would happen here. On the sending side, do the same, and this is where like all this asynchronous JavaScript stuff is making it really easy to read. And I said in this example, I'm not using like DHT or I'm not using any of the fancy node discovery. So I've just manually have my two nodes, P2P ID and other peer, and I connect. I create my dialer and the listener. So in this case, the listener would just be to tell the P2P where to find the party I want to talk to. This is who I am, and so you started with this URL, and so this actually gets printed to the console. You see the listener is listening on this URL. So this is actually so this is I see that whatever I'm printing on the console is not correct. Yeah, because I'm doing this. Actually, this is printed here. Let's see if this works.
Even
No.
plus at the end. Forgot a plus sign.
Down low.
Yeah,
Okay, just undo it.
just line up.
Yeah, that one.
Okay, so this. Yeah, so this is this URL. This is this URL. And basically then like in your distributed hash table you would store this information. It's your IP address. I'm telling it to listen on localhost only right now, but of course you can listen on anything. It says okay, TCP ports 10333. IPFS, that's just the legacy thing because it was only IPFS in the beginning. This is the a hash of the public key you're using to then do this connection handshake. And so then basically, so then what you do is you have this relatively simple message, which is the JSON that you just push with like some stream handling magic. This code, take a look at it in JavaScript. This is not fully implemented. Take a crack at it, see how far you can get it to work. I have a few resources about payment channels and state channels in general. Of course, like the big vision is for state channels to really work is like it should be a network, right? So you can actually you can build payment channels in a way that Alice can send money to Charlie by going through Bob. So if Alice has a channel with Bob and Bob with Charlie, you can go from from Alice to Bob to Charlie in a way that only if you find a link and everyone forwards the payment, it actually happens. So you're guaranteed to like move money from Alice to Charlie, so that they're like atomic in that way. And so then you can have a set of channels with a few well-connected peers and then move value or move assets or anything really that you can put into a state channel through this network.
Is it possible to change path after you opened it?
So what you do is, you see that. I mean, you see there are like a few hubs here, right? And this is actually a big topic of debate. Is like how the network topology will develop. It heavily favors centralized hubs.
You go back to banking systems.
So that's like Lightning Labs, for example, are looking at ways to incentivize like smaller connected nodes to do more routings, because you don't want it to be essentially decentralized. But of course, like the big red guys and like maybe this yellow and right. So this is a guy that has a lot of connections. Like you want to make sure that the network topology develops in a way. But so you can. Basically what you do is you find your route, you confirm it, and then you get a commitment from everyone, and once you get that commitment from like beginning to your final destination, you travel that route back and you move money like in the reverse order.
But can you change route in the meanwhile, even for the next payment, for example?
You could, yeah. So I mean, so if I want to pay Charlie through Bob in one instance and through Eve in another, then that's fine, yeah. There's also, so this is multi-hop payments, like atomic multipath payments actually. So like one big problem with state channels, right, is like you need to deposit money. Like you don't want to deposit and have it locked up forever. And like you need to find a route where if you're making a large payment, you're very constrained with the number of routes in the network that can take it, right? So what you can actually also do is you can split this payment up into like 5 different routes, for example, and you can make this in a way that, again, the payment only happens if all of those 5 routes end up confirmed and get processed. So these are like 2 ways to make this whole network more scalable. I mean, working with so there's like 3 interesting projects that work in like payment networks in general. Lightning is Bitcoin focused. They're doing a lot of awesome work. It's actually way more mature than anything in the Ethereum community, unfortunately. Spankchain is working on more general purpose state channels. So what they're working on is you can make a deposit, but then you can actually do like applications in state channels where like you can do certain actions that is more than just moving value around, but like the channel deposit acts as a way as a deposit to make sure that everyone behaves. And so you can only update state, you can only like unlock your deposits, or the deposit can get paid out depending on like whether you win or lose, or like all these kind of things. And then Raiden is one of the big projects implementing payment channels in Ethereum. Some of the cool things that I think are in the works, and one thing I'm very excited about is when you're doing these payments, it's a big privacy feature. If we can get this payment network to be big enough, right? If there are enough payments flowing around, it will become increasingly harder to route a payment that goes from this guy like through the network to this guy, because it's a whole bunch of balances that get updated throughout the network, and so it's not, you won't know that if it goes through a big node, right, it goes from here through here, then like any outgoing payment on this node could be your payment, and so you lose this capability to track payments from recipient to sender. This actually is, the website is down unfortunately, so I have to make a screenshot. But there's a Lightning Network visualization. I think this might be the test net, but production looks very similar.
Shouldn't take more than 6 steps though. From any point to any point, roughly.
It's do they have a fixed limit of 6, or is that?
No, it's measure normally.
Oh yeah, well, 6 degrees of separation. You mean?
Yeah.
Yeah. Yeah, it should. I mean, you want to find efficient routes. So everyone has it costs obviously to have like network latency, and routers usually get fees. That's how they can monetize on the capital they have locked up. So yeah, you want it to be efficient. but what you can do if you do this is you can actually do onion routing. So I don't know how familiar you are with Tor, but basically with Tor you pick a route through the network, and you encrypt it in a way that you have Alice to Bob to Charlie. So what I do is I encrypt the message that Bob has to send to Charlie with Charlie's private public key, and the message I sent to Bob I encrypted with Bob's public key inside of that message. So what I tell it works with 4 nodes. So if I send something from A to B to C to D, I'm not going to tell. What I want to tell is I'm going to tell A. Let me know when are you? I'm a little over time. I'm already 10 minutes over time.
I'm not
So
a speaker. Just go ahead.
Okay. If I'm holding anyone up, or like if you have somewhere to be, don't feel obligated to stay here. But so onion routing, what you can do is you go from A to B to C to D. What I can do is I can tell B to send my payment to C, and I can encrypt the message for C with a key that B doesn't have, and then B can send that payment to C. And not knowing that the final destination is C, or D, Bob just knows that he needs to send it to Charlie, and then Charlie will unpack their package and then forward it to D, and still not knowing if D will then unpack it and forward it to someone else, or if this is the final destination. So that's why they call it onion, because it's like you peel an onion with all these layers. And so you can do that with payments as well, with payment channels as well, right? So you select a route, you confirm that route, and then you encrypt your you do all of that in private. So you just forward a payment, and even if you're a router that routes payment, you only know like the payments you're routing through. And of course there's a lot of, like, you can do a lot of that with data analysis, timing attacks, and all these things that like still poses a big threat on privacy, but it's a lot better than, of course, than like on-chain payments. Watchtowers is a cool feature. So you have this problem that you can have people trying to exit channels with an update that's not the most recent, and so you need to be constantly online to monitor that the state no one tries to settle the state channel with something that wasn't actually the most recent. Like this watchtowers is a concept from Lightning, where they have a way to let others take watch over these channels, and they get paid a small reward if they detect an early settlement or an incorrect settlement, and then they can submit your message on behalf of you without you having to be online. And then of course there's this whole thing with generalized state channel, where you go away from moving money back and forth to having like sort of transactions. What you do there is you use this deposit as a way to ensure that everyone plays by the rules, but then the state updates, as long as you can encode them in a way that you can then verify on-chain that the state update was valid, whether it's like increasing your balance or decreasing your balance that we had in this example. Like it can be a game of poker or chess or who knows what, right? So you can implement that, and then the deposit is just used to make sure that people play along. But then you can sort of agree on any kind of state in this channel. So yeah, this was mostly it. A few resources, like if you want to see a relatively simple example and you're not too afraid of Go, this rock, paper, scissors demo that Miguel did is pretty interesting, and there are some slides with it as well. He talked about it at the Go developers meetup in spring about this. So it uses the DHT. So when you use this, you can start 3 nodes. Both nodes can connect to one, and then they find each other based on the public key. The Libp2p specs are interesting just on like how it actually works. I've mentioned it before. Protocol Labs really likes to have an abundance of repositories, so this is all split up into like many small packages, but the specs are like sort of a big overview. The other thing like the examples in both the JavaScript and the Go and Rust implementations are pretty good of looking at P2 like at Libp2p. And last but not least, this. The Lightning RFC, they actually call their EIPs bolts, I think, which is pretty funny. So you can look at the Lightning bolts and sort of like what payment channels with in an order of magnitude in complexity and feature set higher than what we just talked about now, actually what this looks like. And of course, like there's an abundance of like general purpose state channel concepts, payment channel proof of concepts online, like specifically Spank Chain, Raiden, Lightning that I would look at, or payment focused. There's also counterfactual, yeah, I think the list goes on and probably changes every month. Yeah. Yeah.
I'm going to ask the dumb question because this is not my thing, but you said something interesting about the nonce not changing. So if it's always depleting my balance, send 1, 2, 3, deplete 1, 2, 3, but have the same nonce. I'm thinking like a high frequency trading situation where, like the second deduction goes through, and then I make a third one, but then I've settled something off chain, and then my counterparty has taken not the last one, but the second last one. Like, is there any? I'm just trying to think. Like, is that a problem, or is that?
I mean, so if your counterparty takes the second last one, that it's their economic loss, right?
Right.
So essentially, they are incentivized not to do that.
Yeah, and because it's back and forth, they would send you something, and you go, "Rock on! I got a $3 or something."
Exactly.
Like that.
Yeah. So that's why, like in practice, you would probably not have to worry too much about this.
Cool. Appreciate
Cool.
you.
Thank you very much, everyone. Feel free to reach out to me if you have any more questions. You look at the code, ask something. I hope this was useful.
Yeah, it was. Thank you.
Thank you.